Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and focuses on the least squares problem and computing least squares solutions and lines of best fit. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. The least squares problem is a mathematical technique for finding the best fitting line, curve, or model for a given set of data. To better understand the least squares problem, let's look at an example where we're asked to determine if a line y is equal to mx plus b can pass through the data points 1, 0, 2, 1, and 3, 3. I've plotted these three data points, and at a first glance, it looks like there is not going to be a line y is equal to mx plus b that can pass through all three of these points. To see if a line does exist, let's write down the equation y is equal to mx plus b and plug in our x and y points. For our point 1, 0, x is 1 and y is 0, and that gives us the equation 0 is equal to m plus b. If we do the same thing for the point 2, 1, we get the equation 1 is equal to 2 times m plus b, and for the point 3, 3, we get the equation 3 is equal to 3m plus b. Let's now see if a solution to this linear system exists. Our linear system is going to be easier to solve if we reverse m and b and write our equations like this. We then put these equations into a linear system, put it in reduced echelon form, and we can see, because we have zeros equal to 1, that we're going to have no solution. We can conclude from this then that no line of the form y is equal to mx plus b can pass through all three data points. Instead, what we're going to have to do is we're going to have to use least squares to find the line of best fit that comes the closest to passing through all three of these data points. To see how we can find this line of best fit, let's take a look again at the linear system that we just created on the last page. Our linear system can be written as a times x is equal to b. Looking up above, we can see that our a is equal to this matrix, and our b is our right-hand side, which is the vector 0, 1, 3. Our x then contains the values b and m for the line that passes through all the data points if one exists. As we saw in the other videos in this series, a linear system of equations a times x is equal to b is either consistent or inconsistent. If it's consistent, the linear system is going to have one or infinitely many solutions x. And if it's inconsistent, it's going to have no solution x. The problem that we just looked at was an example of an inconsistent linear system because we could not find a solution x that contained the parameters b and m for a line that passed through all three data points. Instead, what we have to do is find an approximate solution x hat, and that's exactly what the least squares problem is. The least squares problem is a problem where we're going to find an approximate solution x hat to ax is equal to b. Our solution x hat is going to contain the parameters beta 0 and beta 1, or m and b, just like we saw above. And these parameters are going to give us a line of best fit if the data points lie along a line, or what we call a least squares fit if the data points lie along a parabola. We're now going to walk through how to find least squares solutions. We begin with a linear system of equations ax is equal to b that has no solution. Because it has no solution, we can think of a times x as an approximation to our vector b. The smaller the distance between ax and b, the better our approximation is going to be. Our goal then is going to be to find an x hat that minimizes the distance between b and ax. Mathematically, we can say that the least squares solution of ax is equal to b is x hat such that the distance between b and a times x hat is less than or equal to the distance between b and A times X. The solution is called the least squares solution because the magnitude of a vector u is the sum of its components squared. The term least squares means that we're going to minimize the square root of a sum of squares. Let's now walk through the mathematics of how to minimize b minus a times x. Our x hat is our least squares solution, and we're going to let a times x hat equal b. b, or ax hat, is in the column space of A because it's a linear combination of the columns of A. Because B is an element of Rm, the column space of A is just a subspace of Rm. Our goal is going to be to find an x hat that makes Ax hat the closest point in the column space of A to vector B. The distance between vector B and Ax hat is going to be minimized if A times x hat is the orthogonal projection of B onto the column space of A. Here's Ax hat. Since Ax hat is the orthogonal projection of B onto the column space of A, we know that B minus Ax hat is orthogonal to the column space of A. That means that we can take a column of matrix A, take the dot product with B minus Ax hat, and we know that it has to be equal to 0 because it's orthogonal. We can rewrite this dot product as A sub j transpose times B minus Ax hat is equal to the 0 vector. A sub j transpose is just a row of A, so we can also write this as A transpose times B minus Ax hat is equal to 0. If we multiply A transpose by both of these terms, we get the equation A transpose times B is equal to A transpose A times our vector x hat. This gives us a formula for our least squares solution. X hat is our least squares solution to A times X is equal to B. And the way that we're going to find X is we're going to solve these normal equations for X hat. I've written down 2 steps that we can follow to find the least squares solution to A times X is equal to B. Our first step is that we're going to construct the normal equations for X hat, multiply everything out till we just get a matrix times X hat is equal to a single vector on the right-hand side. Our second step then is to solve this linear system for X hat. Let's walk through an example where we're going to find a least squares solution of A times X is equal to B. And we're given a matrix A and our vector B. Let's call X hat our least squares solutions. And this is an approximation to our vector X. Before we construct our normal equations, I think it helps to look at the size of our linear system A times X is equal to B. Up above, we can see that A is a 3 by 2 matrix, which means that X has to be a 2 by 1 vector, and then B is a 3 by 1 vector. This tells us that X hat is going to be a 2 by 1 vector, and we can let it be X1 and X2. There's 2 steps that we need to follow to solve this problem. The first step is to construct the normal equations for X hat. Let's go ahead and do that. We're going to start with A transpose. So we take matrix A, and the first row becomes the first column. And then we write the rest of the matrix. That's A transpose. And we're going to multiply this by matrix A. And then we multiply it by our X, which we just said is X1, X2. And then on the right-hand side, we have A transpose again. And we multiply that by our vector B that we're given up above, that's equal to 4, 1, 2. Now let's multiply A transpose and A. We're going to get a 1 plus 4 plus 1 in our first entry, and our second entry on the right, we're going to get a minus 2, minus 6, minus 3. In our entry in the lower left, we're going to get a minus 2, minus 6, minus 3. And in the lower right, we're going to get a 4 plus 9 plus another 9. That multiplies x1, x2. And then we can multiply our matrix and our vector on the right. Our first entry is going to be a minus 4 plus 2 minus 2. And then our second component is going to be 8 minus 3 plus 6. On the left, we're going to get a 6, a minus 11, another minus 11, and then a 22. And we have our x1, x2. And then on the right, we have a minus 4 and an 11. Our second step is just going to be to solve this linear system for x hat. Since this is a 2 by 2 system, we can easily solve this by using the inverse of this matrix, or we can just reduce our linear system to reduced echelon form, and that's what I'm going to do. I'm going to write down our linear system. We have 6 minus 11, minus 11, 22, and then we're going to augment that on the right with minus 4 and 11. Notice that our second row has all multiples of 11, so I'm actually going to divide that row by minus 11, and then I'm going to switch rows 1 and row 2. Our first row is then 1, minus 2, and minus 1. And our second row is what our first row was, 6 minus 11 minus 4. We'll circle our pivot and then multiply row 1 by minus 6 and add it to row 2. And we end up with a 1 minus 2 minus 1, and then this becomes a 0. We have a 12 minus 11, which is 1, and then we have a 6 minus 4, which is 2. We now have our two pivots, and we need to get a 0 above our second pivot. So let's multiply row 2 by 2 and add it to row 1. And here's what we end up with. 2 times 2 is 4 minus 1 gives us 3. We then have x1 is equal to 3 and x2 is equal to 2. So we can write down our least squares solution x hat is equal to the vector 3, 2. Let's now talk about how to compute the least squares error. The error in a least squares solution is just called the least squares error. Our least squares error is defined to be the magnitude of vector b minus a times x hat. Let's walk through an example where we're going to find the least squares error associated with the least squares solution, x hat, to the equation a times x is equal to b. We're given matrix A, and we're given our vector b, and we're given our least squares solution, x hat. Let's start by writing down our formula for the error. Our error is going to be the magnitude of b minus a times x hat. The first step in solving this problem is finding b minus a times x hat. b minus a x hat is our vector b, that's 4, 1, 2, minus our matrix A, times our vector x hat, which is 3 times 2. This is going to be our vector 4, 1, 2, minus our matrix vector product. This is going to be the vector minus 3 plus 4, which is 1, 6 minus 6, which is 0, and then a minus 3 plus 6, which is 3. This gives us the vector 3, 1, and minus 1. Now all we have to do is find the magnitude of the vector that we just computed. The magnitude of b minus a times x hat, this is equal to the square root of the components in our vector that we just found, each squared. So this gives us 3 squared plus 1 squared plus a minus 1 squared. This is going to then be the square root of 9 plus 1 plus 1, which gives us the square root of 11. The square root of 11 is then our least squares error that's associated with our least squares solution. Let's now look at how to find a least squares line of best fit. If we have a set of data and those data points lie along a line, our line of best fit can be written as y is equal to beta 0 plus beta 1 times x. If our set of data points lie along a parabola, our least squares fit can be written as the parabola y is equal to beta 0 plus beta 1x plus beta 2 times x squared. Our least squares solution, x hat, contains these parameters. For a line of best fit, it's going to be beta 0, beta 1, and for a parabola least squares fit, it's going to contain beta 0, beta 1, and beta 2. Let's look at an example where we're going to find the least squares line that best fits our given data points, 1, 0, 2, 1, and 3, 3. I've graphed these 3 points on the right, and you can see that there's no line that can pass through all 3 of those points. Instead, what we're going to have to find is what we call a line of best fit that comes the closest to passing through all 3 data points. Let's begin by writing down an equation for this line of best fit. Our equation can be written as y is equal to beta 0 plus beta 1 times x. Let's then set a vector x hat equal to these parameters, beta 0, beta 1, and this x hat is going to be our least squares solution. Let's write down that x hat is our solution to our linear system a times x is equal to b. Now what we have to do is construct a and b from our data points. Our matrix A is going to look like this. We have 3 points, so we're going to have 3 rows in our matrix. Our first column is going to be 1s, and then our second column is going to be our x coordinates, 1, 2, and 3. Let me write that down so that you can remember that. Our first column are going to be our 1s that multiply our beta 0. If we look back up at our equation, you can think of this as being 1 times beta 0. And then our second column contains our x coordinates. Our vector b is going to be our y values. And those are equal to 0, 1, and 3. I'm going to label these as our y coordinates. Our matrix A is often called our design matrix, and our matrix B is often called our observation vector. What we need to do now is find x hat from the normal equations A transpose A times x hat is equal to A transpose times B. Let's start by setting up these matrices. Our A transpose matrix is going to look like this. The first row becomes the first column. And then we have our matrix A. That multiplies x hat, and our x hat is equal to beta 0, beta 1. And then on our right-hand side, we have A transpose, which we already found on the left, 1, 1, 1, 1, 2, 3. And then this is going to multiply our B vector, which is our y coordinates, 0, 1, 3. When we multiply A transpose times A, we're going to get the matrix 3, 6, 6, 14. You might want to stop the video and make sure that you can compute that. And then we have our beta 0, beta 1. And on the right-hand side, we're going to multiply this out, and we end up with a value of 4 and then 11. We now need to solve this linear system, and we can solve it by using Gauss-Jordan elimination or by inverse multiplication. I'm going to choose to use inverse multiplication, but elimination would also be fine. Using inverse multiplication, our beta 0, beta 1 is going to be the inverse of our matrix from the left-hand side on our previous page, and that matrix was 3, 6, 6, 14. And we'll mark up here that we're going to take the inverse of it. And then we multiply that by our right-hand side, which was equal to 4 and 11. The inverse of our matrix is going to be equal to 1 divided by 42 minus 36. That's the main diagonal multiplied minus the off diagonal. And then in our matrix, our main diagonal entries switch, and then our off diagonal entries get a negative. And then we multiply that by vector 4, 11. This gives us 1 over 6, and we can go ahead and do our multiplication. We're going to get 56 minus 66 for the first component. And then for the second component, we're going to get a minus 24 plus 33. In our first component then, we're going to have a minus 10 over 6. And then in our second component, we're going to get a 9 over 6. We're going to now reduce our fraction, and we end up with a minus 5/3 and then a 3/2. Our line of best fit is y is equal to beta 0 plus beta 1 times x. We can then write down that our line of best fit is y is equal to minus 5/3 plus 3/2 times x. The last topic that we're going to go over is how to use QR factorization to find least square solutions. When finding least square solutions of a times x is equal to b, if the columns of A are linearly independent, then the solution can be computed more reliably through a QR factorization of our matrix A. Let's quickly walk through how to find the equation that we're going to need to solve to find our least square solution x hat. We're going to begin by our normal equations for our least square solution x hat. Let's remember that our matrix A is equal to Q times R and that Q transpose is equal to Q inverse. We're going to begin by substituting in that A is equal to Q times R. So we have QR transpose times QR on the left, and we substitute in QR transpose on our right. We're going to simplify the transpose by switching the order of the matrices on both the left-hand side and the right-hand side. We're then going to notice that Q transpose times Q is Q inverse times Q, which is just the identity, so that goes away. And we're left with R transpose R times X hat on the left and R transpose Q transpose times B on the right. We now want to eliminate R transpose, and we can do that by multiplying both sides of our equation by R transpose inverse. And then what we end up with is our equation that we can use to find X hat. I've written down this equation in green so that you can refer back to it. Let's walk through an example where we're going to use the factorization A is equal to Q times R to find a least square solution of A times X is equal to B. We're given matrix A, and it's equal to a matrix Q times a matrix R, and then we're also given our vector B. Let's let our least square solution equal X hat. When doing least squares problems, I think it's helpful to start by looking at the matrix vector product A times X and looking at its size. Our matrix A is a 3x2 matrix, which means that our vector X has to be a 2x1 vector. We can then define X hat to have the components X1 and X2. To find our least square solution x hat, we're going to have to set up the equation r times x hat is equal to q transpose times b. Let's go ahead and do that. Our matrix R up above is 3, 5, 0, 1. And then we just defined our x hat to be x1, x2. And then on the right-hand side, we're going to have q transpose. So the first row of q is going to become the first column of q transpose. And then we have a 2/3 and a 2/3. And then our last column is 1/3 minus 2/3. And we're going to multiply this by our vector b, which is the vector 7, 3, 1. Let's multiply our matrix and our vector on the right. And we're going to get a 14 over 3. And then we're going to add a 6 over 3 and then a 1 over 3. Our second component is going to be minus 7 over 3 and then a 6 over 3 and a minus 2 over 3. If we add all of these up, we're going to get a 21 over 3, which is a 7. And in our second component, we're going to get a minus 9 plus 6, which is a minus 3. And we're going to divide that by 3. And that gives us a minus 1. Let me highlight the left-hand side of our linear system and the right-hand side. I'm going to choose to solve this using Gauss-Jordan elimination. So I'm going to write down our linear system as an augmented matrix, and it looks like this. I'm going to take our first row, and I'm going to divide it by 3, so we get 1, 5/3, and then 7/3. And then we have our second row, 0, 1, minus 1. I'm now going to multiply our second row by a minus 5/3 and add it to our top row. So this is 1, 0, and then we get a 5/3 plus 7/3 is 12 over 3, which is equal to 4. Our augmented matrix tells us that x1 is equal to 4 and x2 is equal to negative 1. So our least square solution x hat is equal to the vector 4 minus 1. This is the last video in this series for this fall, but I plan to add more videos to this series in the future. If there's any videos of linear algebra that you'd like to see, just drop your suggestion in the comment and I'll try my best to make a video on that topic. Thanks for being with me this semester.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.